The title is Game Dynamics in Equilibria, but since usually when this talk is given to a game theoretic or related audience, I don't need to say game. But since here it's slightly different audience, then I'll say Game Dynamics in Equilibria. There's a little echo. Okay. And I know it's not exactly what people do here, but I think it is connected, and you'll see, in fact, towards the end, some surprising connections. And but now, just think of some general thoughts on dynamics and equilibrium in games. And games means more than one person, so more than one brain, okay, at a time. Okay. You can find all this on my webpage, the papers I'm talking about. I want to discuss various things. I'm going to take just one small thing from different places and get some grand picture, or not grand picture, a bigger picture, but anything, if you want to see more details, everything is on my webpage, including this presentation. So let's start with the notion of Nash equilibrium. Okay? John Nash, PhD dissertation, Princeton, 1950. That's the guy from the movie, yes? He proved the existence of equilibria, Nash equilibria, yes? By the way, he's still alive, and in fact, he's getting better every year. That's something I think that brain people should definitely study. It's quite amazing. So, what's a Nash equilibrium? Okay? Well, a Nash equilibrium, of course, Nash called it equilibrium point, not Nash equilibrium, is a situation where every player's strategy is optimal against those of the others. I'm quoting from his PhD thesis. By the way, the PhD thesis is very nice to read. No one could ever get a PhD with such a thesis today in math, in economics, in any field. Okay, it's something, maybe a master, who knows? But that's something definitely not worth of a PhD. Nevertheless, it had a little impact, It's quite amazing. So that's an equilibrium point. Okay. Now, this is a static notion. Static, I mean, it says if you are there, you are there. It's a situation where something happens, it's defined in a static way. Question, what happens if we talk about dynamics, about processes that approach it, converge to it or something? Clearly, something saying something is optimal, then that suggests, okay, if people optimize, if people do this, we should get there. Okay? So, let me tell you a fact. Okay? And now, since I know there are computer scientists here in the room, let me tell you what I mean by a fact. Okay? So, once upon a time, I do write papers with computer scientists. In fact, you'll see one here. So, there used to be theorems and propositions and lemmas. Then we started to be claims. Okay? So, claim, I was told, is something that less than a lemma, you still prove it. Then lately there are facts. Fact is less than a claim, and you don't prove it. Okay? Which of course increases the probability of it being false. Okay, but that's what a fact in computer science papers is. Now this is not such a fact. This is a real fact. I'm telling you something about the state of the art of game theory in 2011, which is more than 60 years after Nash. Okay, there are no general natural dynamics leading to Nash equilibrium. So I'm describing you the state of the art of game theory today. Okay. But now let me explain what is written here. I think there are no, everybody understands, so let's start with general. General, I mean in all games, or in a wide enough variety of games. If we talk about specific classes of games, then, like zero-sum games or potential games, doesn't matter what those things are, but in specific classes of games, then one can find such dynamics that lead us to Nash equilibrium, okay? And the three dots there, in fact, turn out to stand probably for zeros of classes. No, maybe one or two more classes. In fact, it's very few classes of games for which this statement is not true, which means there are natural dynamics. Okay. So what we want is something that we don't know what games we are going to play, we don't know what interaction will be. So something that works only if the game has a very, very specific structure. Well, it's good if the game has a specific structure, but it's not good in general. So something that works in general games. Okay, let's go to leading to Nash equilibrium. What do I understand by leading to Nash equilibrium? Leading to Nash equilibrium means that I know the dynamic to get to the Nash equilibrium or the small neighborhood of the Nash equilibrium and stay there. Okay? something that visits the neighborhood of Nash equilibria and then goes away and starts wandering around and then perhaps comes back and visits again, so that doesn't count. That's not converging to Nash equilibrium. Convergence to Nash equilibrium means that you get there. And once you are there, you stay there, at an equilibrium or close to it. Okay? Now we come to natural. Okay? So, if you notice, natural is in quotation marks because I don't know how to define it. Let me say some properties of what I want those dynamics to have. So I want those dynamics to be something called adaptive, which means I want the players, I want the participants to adapt to what's going on, to react to what's going on. Okay? Perhaps in an improving direction, but perhaps not, but something in that general idea. I want the dynamics to be simple and efficient. In what sense? For instance, in the amount of computation one has to perform at each step. So dynamic means you play today and tomorrow and so on. Now, if every time you have to decide what to do, you have to solve a non-linear fixed point problem, I don't know how many of you ever solved even one. But doing it every day is clearly not something people do. So maybe you could prove some nice theorems with it, but that will not be a natural dynamic. Okay, so natural, I mean something that people do, something that tells us something about the world, something that is not artificial. So we want the computation to be reasonable. Okay? For now, I'm extremely vague, but I'm going to make some of these things more precise. Then I want the time it takes to reach equilibrium to be, slightly less than the age of the universe, or 2 to the power of the age of the universe. I mean, so having some dynamics converging to equilibrium, but they take longer than the age of the universe. Okay, you have proved the theorem. What does it tell us? Okay. We want the information that people have to be again reasonable. We don't know everything that's going on in the world. We hardly know what happens in our small neighborhood, whatever that means. So we want the information to be reasonable. So again, those are different coordinates of what I would call simple and efficient, or what I would call natural dynamics. Again, there is no definition, but we'll try to see what those properties mean. Okay? Now, all of these sometimes are under the heading of bounded rationality, which means we can't compute everything, we can't complete our best reply to everything and so on. That's our rationality is bounded. We can't, we won't, we don't, whatever note you want to put at the end. Okay? Now, to understand what the natural dynamics are, let's see some examples of dynamics that I consider not natural. Okay? Exhaustive search. Now, if we find equilibrium, just, for example, start going cell after cell in the matrix and check whether this is the Nash equilibrium until we find one. Okay? Now, that's good. Find the Nash equilibrium, but that doesn't tell us anything. That's not the dynamics. That's not the natural dynamic. Now, you could do it a little more sophisticated. For example, choose a cell at random and then find out if it's equilibrium and then move at random. It's still exhaustive search. Okay? So here's an example of exhaustive search. Without words. I hope you can read. It works, as you can see. Okay? Well, I saw this cartoon someplace, but despite Google and internet and everything, I could not find it. But I did find a place where you can get Einstein with a blackboard where you can write anything. So I reconstructed it. Okay, but so it's not my idea, but I think it's incidentally, if you go to the library here, that's a manuscript from Einstein's manuscript. I mean, L doesn't work, let's try E, it's not this equation, it's that one. But remember, it was not word processing there. You write something, there is no way to get rid of it with just delete, yes? So, okay. So, let's go back to our story. So, exhaustive search is not something I counted as natural, okay? Using a mediator, having somebody that you go to him, or her, and everybody tells that person everything they know and everything they want and everything, and that person tells everybody what to do, and everybody does it. Okay? That works in stories, maybe. I don't know in real life, but it works. Okay? Another thing, again, this comes from computer science. Everybody could broadcast what they know and so on to everybody, and then perform a joint computation of finding an actual equilibrium. Again, those are not natural things, but they are used to prove theorems. Right? So that's okay. It is perhaps something a little more subtle. What I call fully rational learning. Now, what's fully rational learning? Fully rational learning is the following situation. People start with some beliefs. Okay? Beliefs over everything. Over the state of the world, what games they are playing, who are they playing with, what the other players want, what the other players do. Now, again, this is dynamics, so the game is played repeatedly. Okay? So the kind of objects we are talking about is, for instance, what other players do in this repeated interaction, in this long-term interaction. Now, a strategy there is a very complex object. It's what you do first period, what you do second period as a function of what the other guy did previously, what you do in the third period, and it's getting bigger and bigger. It's a huge object. Now, so those could be very, very complex strategies. Now, people start with beliefs over the set of all such objects. I mean, that's very, very hard. Yes? Then what do they do? Okay, then they observe what happens and they say, aha, the other guy did this, so I have to update my belief. Base tells me how to do it, I go and find the numbers, and then what do? I compute what should be my best reply, or better reply of something. I mean, nobody does this. Okay? But, so again, this requires real dedication to rationality, you know, and all day to do computations and compute and optimize, etc., etc. So, there are some very nice stories regarding what I call fully rational learning, on possibilities and impossibilities and what is needed and so on. But I'm not saying that this is not interesting. It's very interesting, but this is not what I call natural dynamics. That's all. So I'm not saying something negative, that that's not an interesting topic. It's very interesting and one can learn in fact a lot. But this is not what I'm looking for. Okay? So let's see what I'm looking for. So again, remember what I said about natural. Okay? I gave you some keywords. Yes, not exactly definition. So I want something that is adaptive, and I want something that is simple and efficient in terms of various coordinates, computation, time, information. And let's start with the information, with this coordinate. So what would be simple and efficient assumption on information? Okay? So here is the assumption that I want to take, and that is that the player knows only what he wants, he or she wants. What? Okay? Players, again, I say all the time players, just participants, whoever you want, yes. But so just don't know the payoff functions of the other players, okay? I mean, I hardly know what I want, okay? Some people know very well what they want, okay? Maybe they get it, and maybe that's not what they wanted, but that's beside the point, yes? I'm getting psychology now. But, you know, maybe I know my own utility function, maybe I know what I want, but for sure I don't know what other people I interact with want. I can see what they are doing. I can try to deduce from that what they want, what really their objectives are, but I don't really know. Okay? Now, this assumption turns out it's a very natural assumption, and dynamics satisfying this are called uncoupled dynamics. That's a name that we gave to this kind of dynamics. And if you think it's a new idea, it's not. I mean, for instance, let's start with computer science. What is called distributed is essentially the same idea. Yes, each computer knows only its local information. Okay, we have a network or something like this. In what's called mechanism design, this heuristics got the Nobel Prize a couple of years ago, called it privacy preserving. Okay, that's an assumption. Decentralizing economics. All these things are more or less the same kind of idea that people know information about themselves and very little about the others. Okay. Nevertheless, what happens now? Okay, just to make sure that everyone understands, I am going to use some notation, just very, very little, but just to make it sharp what exactly I mean by uncoupled dynamics. So let's take an n-person game, so we have n people interacting, or n players. Okay, it's called person, but those could be anything. Could be genes, could be computers, could be whatever you want. Now, let's call by A super I the action of player I. And so player I chooses an action in the set I. As you guys see, fine, I'm not doing anything fancy here. Okay, it's the simplest possible thing. And what makes it a game is that the payoff of player I depends not on just what he does, but on what everybody does. Okay, so that's what makes it a game, rather than a simple optimization problem where what I get depends on what I do. So what I get or gets depends on what everybody has done. Okay. Now let's talk of dynamics in a very simple framework of discrete time. So time is 1, 2, and so on. One can do it continuous time, doesn't matter, same things, but for presentation let's do discrete time. And so dynamic consists in player I at time t choosing a certain action in that set of possible actions. Okay? So A is the action chosen by player I at time t, And of course, he could choose it using some randomization, sigma IT. Again, that doesn't really matter. Anyway, I'm not going to get into too many details. Now, I want to capture this idea that the dynamic depends only, is uncoupled. Namely, that the way people act depends only on their own utility function and not their own payoffs, and not on the payoffs of the others, it's just because they don't know. Okay? So, to do that formally, let's fix a set of players and let's fix their action sets. Okay? So players are 1 to n, and their actions, the set of actions, A1, A2 up to AN. Okay? Now, what would be a general dynamic? A general dynamic would say this. So sigma IT is what player I does at time t. Okay? It's a randomization he uses, or AIT, whatever. It doesn't matter. So what player I does at time t is a function of two things. Of what has happened until that point, the history, I call it history. Maybe not the full history, maybe what he remembers of the history, he has short memory, or maybe he didn't observe anything, but history in general. And again, of course, in different games, it's going to act differently. Okay? So in general, what player does depends on what has happened up to that point, and depends on which game is played. So, since we have fixed players and strategy sets, then here I just have to put the collection of payoff functions. Okay? So, what player I does at time t is a function of the history and of the n tuple of payoff functions. That's a general dynamic. What's an uncoupled dynamic? Exactly the same, except that instead of here having all payoff functions, I only have UI. Now, what does this mean? Okay? So let me say it in different words. Suppose I have two, let's say it in an equivalent way. Suppose I have two games where my payoff function is exactly the same, but my opponent's payoff function may be different. I don't know. Okay? What uncoupled dynamic requirement says is the following. If in the two games the history of play up to now has been the same, I must play the same thing tomorrow. Because I have the same history, and from my point of view, it's the same payoff functions. The fact that it may be a different game, I don't know. Okay, so I have to play the same. That's it. If you want for mathematicians, it's a measurability assumption. Okay, but that always scares people off, so forget it. Okay, but that's but that's the right thing. It just depends only on UI and not on the payoffs of the other players. Now, this sounds like a very innocuous assumption, but okay, let's see what we get. So what would be okay? So what would be, you know what, here is a question. Can somebody give me an example of a dynamic which is not uncoupled? Okay, can somebody give me an example of a dynamic that is uncoupled? Let's start easy. Come on. You are allowed to participate.
Do the same thing every time.
Very good. So, for example, always play the first strategy. Okay, always. That's clearly uncoupled. It doesn't depend on the payoff functions of the others. It also doesn't depend on mine. Okay, very good. That's very simple. Okay, anything a little more sophisticated. Okay, so I'll tell you one. Okay, so I just look at what has happened in the past, and I best reply to it. I play the best against let's say what has happened yesterday. Okay? So what I have to know is what players have played yesterday, and I have to know my own payoff function, and to maximize my payoff function, find what action maximizes my payoff. Okay? That's clearly uncoupled. I don't have to know what the payoff functions of the other players are. I have to know what they did, which is part of the history. I have to know what my payoff function is, and I just react. I could take his best reply, I could take better reply, I could take lots of other things, I could react to the average of what they did in the past, lots of things like this. All of these are uncoupled. In fact, now let me come to the second question. Can you think of something which is not uncoupled? It may sound like Moliere, you know, that you have been talking uncoupled all your life, you never knew it, yes? You've been talking prose all your life, but in fact, most dynamics you think of are uncoupled. Okay, most natural dynamics is people react in some way, given their payoff to what has happened. They adjust somehow. Okay? Here is an example of a dynamic which is not uncoupled. Okay? We compute the Nash equilibrium of the game. Let's say the first one in some order, lexicographic order, and everybody plays it. This is clearly not uncoupled, which means coupled, because in order to compute the Nash equilibrium, we have to know the payoff functions of everybody. It's not enough to know your own payoff function to do that. Okay? Of course, you could say, okay, let me, okay, now something else which is not uncoupled, just to have another example. I'm going to say, okay, I know what has happened yesterday. I'm assuming that say just two players for simplicity, that the other player is going to play best reply to what I did yesterday, and I'm going to play best reply to his best reply. For this, I have to know what his best reply is, so I have to know his pair function. And then I do a best reply to his best reply is my pair function. Okay, look, I haven't seen many people doing that. Okay, yes.
But at the Nash equilibrium, you don't have to. I mean, you only to get the next step. You only need to maximize your own.
Very good. To check that you are at the Nash equilibrium, you only have to know your own pair function. To check that you, from your point of view, but you still don't know, even knowing whether you are at the Nash equilibrium or not. You can't know it. You can know that you are maximizing, but you don't know if the others are maximizing, and you think, oh, we are at the equilibrium, very nice, now I can relax. Suddenly the other people start moving away because they were not getting the best payoff, and you are not there. So you cannot, by yourself, even know that you are at the Nash equilibrium. Okay, so now, let's see what this uncoupledness assumption is. As I said, natural dynamics being uncoupled, it's most dynamics that one thinks of are uncoupled. Okay? So, the simplest possible uncoupled dynamic is essentially what you suggested, which is always play top, always play the first action. Okay? That's clearly uncoupled. But clearly that's not going to react to what's happening, and clearly has no hope of converging to equilibrium unless the equilibrium is there. Yes? So what would be the next simplest? So the next simplest would be something which essentially I mentioned already, where you really use the minimal amount of information, namely where people react only to what happened the previous day, yesterday. That's the minimum amount of information. Okay? So formally what this says is that what player I does at time t depends on at minus 1, that's what everybody did yesterday, the period t minus 1, and his own payoff function. Okay?
But the payoff function is a function of all the actions.
Right. It's the payoff function that maps actions to payoffs. It's a function. It's a whole function
of all the players.
Sorry?
But it's a function of the action of
yeah, so I know the description of the game. I know what I will get in every possible situation.
I'm just asking, the argument of UI is A assigned to
No, it is a function UI. I'm allowing you to know the whole function, not just what you actually got as payoff yesterday. Not only the amount of money you got yesterday, but all possible payoffs you could get from every possible combination of actions. This requirement is an even stronger requirement. You don't even know what you would get in other situations. That we call completely uncoupled, by the way. But you'll see that already, so it's a much stronger assumption. But even with a weaker assumption, you'll see that we already are in trouble. So, but that's a very good question. So that's definitely something to look at. But let's first allow them to know what would be the possible payoffs in all possible situations. Okay? So they know the function, that object. Okay. So these are dynamics. And what happens is that we call this one recall. So you only remember what happened the day before, one day back. Okay, memory one. But I like to call this recall because memory sometimes. In memory, I can put different things. I mean, I have a very small memory, but it doesn't have to be of yesterday. It could be of 10 days ago. Okay? Whereas recall means exactly one period ago. Okay? Also, notice here again, it's very technical, but okay, you can ignore what I'm saying now if you find it too technical. There is no index t here, which says that this is stationary in time. Because if you allow the calendar time to matter, you can encode into this anything you want, and that becomes this. Okay? Now, I want to look at essentially, so think about a simple game. Let's assume that I'm looking at a game that has a pure Nash equilibrium, which means that it's a combination of pure actions. Let's forget randomization, to make it simple, just for the presentation. Yes? So let's assume we have a game where there is a pure Nash equilibrium. There is a combination of actions, there is a set in the matrix where everybody is best replying. Okay? Assume that it's something like this. Then can you get this with strategies like this? Well, that should be easy. Everybody keeps best replying to what happened last time, and then finally remaining must converge, right? That's quite clear. Except that no one has ever been in my class here, which means that whenever I say it's quite clear, that means it's false. Okay? So this very clear statement is in fact false. Not only this doesn't work, nothing of this kind can ever work. Okay? So here we have an impossibility result that says the following. No matter how smart you are in devising some dynamics that are uncoupled, which means everybody knows, each player knows only his own payoff function. And every player only can look at what happened one period ago. Okay? Not further in the past. Then there are no uncoupled dynamics with one recall that gives us convergence of play to pure Nash equilibria, of course, in games that have pure Nash equilibria. Yes? There is a counterpart with mixed, but let's not talk about mixed equilibria. So, you could say, maybe let's not play best reply, let's play second best, maybe that will work, or maybe nothing can ever work. Okay? So, if you require uncoupledness, one recall, no way that you can get.
Student said that in all games.
Sure.
If
Now,
game
some games, look, take the game where everybody gets payoff of 7 no matter what. Then, of course, you are going to converge to pure Nash equilibrium no matter what you do. So there are games that are going to get convergence, but not in all games. Remember, one of the conditions I wanted, not to have a restricted class of games, but you have to have very general games. Now, this is not going to be a pathological game that this. In fact, where is it? Okay, here is an example of a game, and I can bring you lots and lots of examples, generic and so on. I'm not going to get into the details. No, I'm definitely not going to get into the details of this. So I'm going to skip that. It's in fact a quite neat proof. Has to do some errors, but anyway, okay, drawn correctly and so on. Okay. Essentially has to do, okay, I'll just give you some hints. Why uncoupledness is such, turns out that it's quite powerful. Because what uncoupledness says is, so suppose you have a dynamic that converges to Nash equilibrium. Now, you know your own payoff function. If currently you are not best replying, that cannot be Nash equilibrium. So, but if you are best replying, could be a Nash equilibrium. You don't know about the others. Now, you better stay there. So if you are currently best replying, you better stay there, because if you move, you don't know what the payoffs of the other players will be. Maybe this was the only Nash equilibrium of the game. And if you keep moving, you are never going to stay there. Remember, converging means that you reach it and stay there. So if you are best replying, maybe say only Nash, don't move. That puts some requirements on the dynamic, and that turns out to be contradictory to the fact that you can reach Nash equilibrium. Okay? It's a nice answer. Now, suppose we are increasing the recall. How long do I have? Until when? 2, 3, 4? No. I won't go far. Let's do 2. Recall of size 2. Well, it turns out with recall of size 2 you can do it. Namely, there exists uncoupled dynamics that have recall 2. Recall 2 means I remember what happened yesterday and the day before yesterday, that are going to reach Nash equilibrium in any game that has a pure Nash. I'm talking about pure Nash. And I'll tell you what those dynamics are. Very simple. So, every player remembers what everybody did yesterday, let's say, and the day before yesterday. So there are, say, n players, and so there is an n tuple of actions yesterday, and n tuple of actions the day before yesterday. There's this window. Okay? Now, here is a strategy that player I uses, for any I. Player I looks at what happened yesterday and what happened the day before yesterday. If it's exactly the same combination of actions, then he looks at his own action and asks, am I best replying? If the answer is to what everybody else did. If the answer is yes, I play it again. Any other situation, I play something at random. Say uniform distribution. That's it. That works. Why? Because once a pure Nash equilibrium has been played twice in a row, everybody checks, everybody finds out that he's best replying, everybody repeats it. So next day we are going to have the same n-tuple repeated, the window moves, and this goes on forever. How are we ever going to get to that? Well, that's randomization. Okay? So we are going to reach this eventually and stay there forever. Now, that's an uncoupled dynamics, it's recall of size 2, and it works. Okay? Here it's totally forgetting. Okay? Now, that's very good. Why is it good? Well, it's good because it's very simple. I could describe it to you in words. I hope you also understood it. Yes, but I'm assuming that. It's quite simple. What's bad about it? Well, it's exhaustive search. In fact, I have to get to it by chance twice in a row, okay? Which takes a long time, maybe. And all players must use this kind of strategy. There must be some coordination between the players, otherwise it won't work. If I'm doing that, but somebody else is looking, when there is a repetition of 3 or something else, it's not going to work. Okay? We have to do the same kind of thing. Okay? And as I said, since we have to get this repetition twice in a row, if it's a big game, it's going to take a long time. Okay? And my daughter said you can't have good bed without the ugly. So the ugly, but I don't know. There is nothing ugly here. That's another Sergiu, by the way. Misspelled name, yes. Young people probably don't know what I'm talking about. Okay, so let's go back to the facts. So that said, there are no general natural dynamics leading to Nash equilibrium, and we talked about information and the condition that the information should be simple, efficient, natural, whatever you want, was this uncoupledness condition. Also notice that the computation was very simple because of the finite recall. You only recall what happened in 1 period or 2 periods, so that says that the computation must be simple. You only have very limited information. Don't remember the whole history. Okay? So now I want to talk about the third coordinate, which is time. Especially since time is running short, we better get to that. So time says how long does it take to reach equilibrium? Okay? So remember, the natural dynamic, one of the requirements is that it should take a reasonable amount of time, not too long. You want to get there, otherwise it's not good. Okay? So what we want is to estimate the number of time periods it takes to reach a Nash equilibrium by some dynamic. How do you do that? Okay? That's a difficult question. Turns out, however, that there is a beautiful tool to use it, because an uncoupled dynamic reaching Nash equilibrium is like a distributed computational procedure. Okay? And computer scientist people here, I hope you know what it is, but even if you don't, I'll tell you. So I'll tell everybody what it is. It's in fact a simple idea. And the tool that analyzes the complexity of distributed computational procedure is called communication complexity, not computational complexity, which is the standard P equals or not equal NP. Okay, that's not what I'm talking about. So I've not solved the problem whether P equals NP. Okay, no. I'm talking about communication complexity. Everything starts with C, which means there's a high probability at some point I'll say computational, and I mean communication. Okay, but I'm talking about communication complexity. Now, what's communication complexity? So here it is. It's very simple. Okay, what's a distributed computational procedure? We have a number of participants, and each participant at the beginning has some private information. Okay, and then they exchange messages, and they don't exactly care how. Synchronously, asynchronously, it doesn't really matter, just a constant factor which will never matter, and at the end they reach an agreement. Okay? For example, you have a number x, I have a number y, and at the end we have to know what x plus y is. Okay? How do we do that? Well, one way is you tell me your x, and I'll compute and give you the result. Yes? That's dangerous because I'm sure you make an error, so perhaps I give you my y, you compute and give me back, or perhaps you tell me your x, I tell you your y, each one does its own computation. Either way, at the end we'll know x plus y. Okay? Question is, how do we do it fastest? What's the minimum amount of information we have to exchange in order to find out this result that we are reaching for? Okay? Now, for x plus y it's quite easy, but one can do it for various such functions. Okay? So, we have inputs which are private, we have outputs which is common, and the communication complexity tells us what is the minimum number of rounds or the minimum number of bits, doesn't matter, again, it's a constant factor, that is needed in order to get from the private inputs to the common output. Okay? And this has been, I think the first is Yao responsible for that, and the book on the subject is Noam Nissan here and Kushilevich, beautiful book on communication complexity, so you can, everything you want to learn about it and more. And now, what does it have to do with our problem? We don't compute it. Okay? Yes, it is. Because an uncoupled dynamic leading to Nash equilibria can be regarded as the following. At the beginning, each player knows only his own payoff function, but not the payoff function of the other. That's a private input. Then they play the game. So when they play the game, it's essentially communication or messages go across because I can see what you do, you can see what I do. We can translate this into bits of communication. At the end, we all play the same Nash equilibrium. That's a common output. So communication complexity will give us a bound on the minimal number of rounds needed to go from the private input to the common output, which is the Nash equilibrium. Okay? And I don't care. And this is, again, those are going to be bounds that are coming from communication compensate. I don't know what the dynamic is. I don't care if people are optimizing, whatever they do. There's a certain, you cannot do it faster than so and so. That's the result. Okay? Those are very hard bounds. Okay? Okay, so now, following the standard way of classifying things that are polynomial, I'll call them efficient. Things that are exponential, I'll call them not efficient. Okay? Things that exponential grow too much. So I'm going to say that an uncoupled dynamic is time efficient if the time it takes is polynomial in the number of players. So as the number of players increases, the amount of time it takes grows polynomially. Okay? Rather than exponential. Exponential is too long. Okay? We'll never get there. Okay? So here is another impossibility result. There aren't such features. No matter what you do, you cannot find uncoupled dynamics that reach Nash equilibria. Again, here this is stated for pure, but it works for anything. Pure, mixed, Bayesian, whatever you want, any notion you want. So let's go pure. Okay? So there are no uncoupled dynamics that reach Nash equilibrium in games that have Nash equilibrium, of course, where the time it takes is polynomial in the number of players. In fact, so this is work with Ishai Mansour that some of you may know from computer science in Tel Aviv. In fact, it turns out that the amount of time, not only it's not polynomial, is exponential. So not only that we are showing that this cannot be polynomial, it is exponential. Okay? It's like exhaustive search, because exhaustive search is like going step by step. That's going to take exponential time. Yes, if we have n players, every player has 2 actions. Let's say let's make it simple. There are 2 to the power n action combinations. Okay? N players, each player can play 0 or 1. So the number of possible action combinations, what everybody does is 2 to the power n, exponential in n. So going one after the other and checking, is this Nash equilibrium? No. Is this? No, no. Okay? Then we find it, but it's exponential. And in fact, that's the best you can do. Within a factor of 2 or 4, we don't care about constant factors, but that's the best you can do. That's what this result says. So this is really a tough result, yes? It says no matter how smart you are, no matter how much you look, you can't find dynamics like this. There aren't any. It must take the amount of communication needed there is very large. No. Here there is no restriction whatsoever. Just as uncoupled dynamics. So theorems that I think are precise. I mean, even though I'm not saying, but no, just any. Use whatever you want. Because this tells you that the amount of information that has to go across is bounded from below by something, and you can't do it faster than that. I don't care about it. Okay. Well, let's not get into that. Okay. So, yes, so remember what we started. We started with this fact, which I told you, this is the state of the art of game theory. Okay? That there are no general natural dynamics leading to Nash equilibrium. Okay? Now, I hope that I convinced you that this fact, in fact, is a theorem. There just cannot be objects like this. It's not that game theory, I mean, that's very good for our self-esteem. It's not just that we are so stupid that in 60 years we could not find something like this. By now we know there aren't such objects. Okay? That's why I couldn't find it. So that's reassuring, So, if you put all this, and again, I just gave you a few results. I mean, there are much more. Okay? But I just gave you a few results. But when you look at the whole picture, it's consistent. Okay? Whichever way you look, you cannot get, there are no general natural dynamics within the Nash equilibrium. Okay? It's a result. It's a theorem. Okay? Okay. Now, okay, so I just moved it up. But now, let's think a little. Okay? Some computer scientists should have protested. No one wants to protest? You're allowed to. I cheated a little. Well, I didn't cheat. I mean, everything I said is correct in terms of interpretation. Maybe I'm asking too much, because let's go back to the last result. We have n players. Let's say every player has just 2 possible actions. Okay? So we have 2 to the power n boxes, 2 to the power n action combinations that could be equilibrium. Okay? Now, what's the size of the data? The size of my payoff function that I know. What is it? In each one of these cells, I must have a number, my payoff. So I must have 2 to the power n numbers. That's what I know. So the size of the data is exponential in the number of players. So the size of the data is exponential in the number of players, I want to solve the problem in something that is polynomial in the number of players. That's asking too much. That's wrong. Yeah? Okay? So, again, the size of the data, the size of the individual, what everybody knows, is exponential in n. And I wanted a dynamic that will solve the problem, whatever the problem is, where the data is exponential in n, and the solution will take something polynomial in n. That's too much. If we can, I mean, it's not the right requirement, right? Okay? Well, so let's look at something else then. Let's look at another solution concept, which is correlated equilibrium. Correlated equilibrium that has been introduced by Aumann, yes, in 1974. And what is the correlated equilibrium? Well, it is like a Nash equilibrium, except that before the game is played, people or players receive some information, some signal. They know something. That does not affect the game. Very important. If that information is going to affect the payoffs in the game, that's a different game, that's something else. But there is some, for example, they observe the weather, it's coldest day in Jerusalem, yes, that's something we all know. So perhaps, that matters. Now, if it does not affect the game, how does the weather matter? How could the weather matter? Well, it could, because we could take it as something. I have to decide what to play, and Jonathan has to decide what to play. Maybe we are using those signals that we get, that have nothing to do with the game, in order to decide what to do. For instance, if we are supposed to play a game, and it's almost going to snow now. It's not, but let's assume it is, we want to go home and so on. I'm sure we are going to play the game much different. It's a nice day, with lots of sun and a pot of wine here. We have time, we can play the game for a long time. Okay? So we both of us are going to play differently in different situations. So those external signals that do not affect directly the game may well be used by the players to decide how to play the game. And then we introduce various correlations among what the players are doing. And that's the idea of correlated equilibrium. Okay? So, here's the definition again, and just get some examples. So if the signals are independent, statistically independent, if his signal and mine are statistically independent, we are back to Nash equilibrium. There is nothing new. We can't get anything beyond Nash. Okay? But if the signals are, say, what are called public signals, what are called sunspots, if we both observe the sunspots, on the sun, or the weather, or we both read the newspaper and find out, something, and that's common information. It's public information that we both have. We could use it to decide what to do. Okay? What this boils down to, then, are complex combinations, averages of Nash equilibria, with some probability one Nash equilibrium, with some probability another Nash equilibrium. Okay? Now I have a nice example. Okay, why don't I tell you that? Butterflies. Okay, England. Dark forest in England, there are butterflies. Believe me, there are. Okay? Here is the name. Speckled wood or whatever it says that I can't even read. Okay? Those are real butterflies. Okay? So what happens is that even in England, once in a while, there is a patch of light that succeeds in going through the foliage. There is a ray of light in a small patch on the ground. Happens even in England. Not often, but happens. Now, what is it good for? Well, remember, it's dark forest, England. Now, Mr. Butterfly and Madame Butterfly have to meet someplace. Where are they going to meet in the dark, cold forest? Where the patch of light is. So what do the males of this species do? They occupy such a patch. And that's where Madame Butterfly comes, of course, because that's where the male is. Okay? Now, what happens if two males come to such a place? Okay? So, they can be very polite. You stay, no, you stay, the Polish kind of butterflies. Or, sorry, not polite. Sorry. I want to do another job, yes. Or if they could fight. Now, butterflies fight, sure. They start going up and down, flying one next to the other and so on, and this is fine. But remember, this is dark, cold forest. You better save your energy. You have very little. You better save it for Madame Butterfly, not for doing this. Okay? That's not the right thing to do. So they can fight, or not. So turns out that the following happens. Nothing very simple. First comer stays, and if somebody comes and there is already somebody there, goes away. So say, oh, sure, the one that is there is the big butterfly, and other small butterfly sees the big guy, he goes away. So somebody, a biologist, I think Nick Davis, if I remember correctly the name, I got this from Adi Schmidt, did the following experiment. He took resident males that have a patch of light, took them away, and put butterflies that had no patch of light. And what happened? Exactly the same, which means those that were there stayed, and those that came went away. Which means it's not the size of the butterfly, it's whoever was first. So it's a very beautiful and very simple coordination device. In fact, you can find it in many places, and it is a correlated equilibrium. You could ask, there is another correlated equilibrium. The second one always, the first one goes away, the second one stays. But there is an advantage, there is some advantage to the first one. You get some energy from the sun. So, okay, it's a little more complicated. But this is an example of a correlated equilibrium. Okay? Okay, I won't tell you about what these are. Boston Celtics. If you want to ask me about basketball, NBA, I also have a correlated equilibrium there for the Boston Celtics. You have to tell you that I didn't waste my time at Harvard. Okay? But here is something very important to understand. I mean, signals are all around us. Okay? And we all see the sun, we all see the weather, we all read the newspaper, there are so many signals around us. Now, they will find their way into the notion of equilibrium. I mean, assuming that they don't enter equilibrium, they are just there, it's really an extreme assumption. So, what it says is really that correlated equilibrium is a very, very natural notion. Okay? In fact, now there is a whole literature on that, has to do, I mean, okay, I'm not going to get into that, but
if I can ask,
sure.
Is a clock enough?
A clock? No, the question is not what the signal is, but what Jonathan knows about it and what I know about it. The correlation. Okay. A common clock is sufficient for some things, but not for, okay, I didn't tell you.
So what is needed?
No, sorry, I'm missing here a slide, or I just went, sorry, I went here a little too fast. Oh yes, it's here, sorry. So here I talked about independent signals, which is just Nash equilibrium. Then I talked about public signals, which is like the clock. There is something even more interesting, which is where we get signals that are not independent, not fully correlated. Okay? There is some positive or negative correlations in the signals. Then we get something that is completely new. Okay? Which in fact is what was in the other slide that I didn't get into details, because it's going to take me beyond the time that I'm allowed.
What is public signal?
No, public signal is common signal. The signal that is observed commonly by everybody. So a clock is okay. Weather is okay. But that only leads you to converge combinations of Nash equilibria, which is not far from Nash equilibria. But there are correlated equilibria. The interesting ones are when you get something which is much better than all Nash equilibria. And that you get by having partial correlation between your signal and mine. Okay, and this I didn't talk about, but that's what the interesting thing is. Okay.
What is the public signal with the butterfly?
Who was first? Who is the resident? They both observe. I mean, when you come, you see there's somebody there or not. That's a public signal. Okay. Okay. Now, what happens if you look at dynamics for correlated equilibrium? Let me give you a result. Theory. There are general natural dynamics leading to correlated equilibrium. What do I mean by that? Okay. Oh, sorry. Let me. For example, something called regret matching. For example, I'll tell you in a moment what it is. Not yet. For example, a whole class of something that is called general regret-based dynamics. Okay? And what are these things? And then I'll tell you what the statement says. So regret is the following kind of measure. Is the increase in payoff, have you done something different in the past? How much better could I have been if I would have done something different in the past? Again, I'm not getting into details, there are different ways to define it, but roughly tells me that if I would have done something different, I would have gotten a higher payoff, a much higher payoff. I regret not having done it. If it would not have affected my payoff, or I would have lost, then I have no regret. Okay, that's very simple. And the matching says that the higher the regret, the higher the probability that I would play that next time. So I say, oh, why did I do that thing last time, or I didn't do that thing in the past? Then I could have now been a millionaire. Then the more tendency I have to do it. Well, if I would have done this in the past, I would have gotten only 1 shekel more. I don't know if I'm going to do it today. No prosper. So the bigger my regret, the more my propensity of playing it tomorrow. That's regret matching. Okay. Now, roughly speaking, there are many variants here, and with this kind of dynamics, what we have Those dynamics work in every game. Every game, doesn't matter what it is. It's natural in the sense that it is adaptive. Yes, I mean you are reacting to your regret. The bigger regret, the more you tend to change to something, to the other, to the alternative. Okay. In fact, it has lots of cousins. Okay. I'm supposed to end. I was supposed to end 10 minutes ago, or no? What?
You have 10 more minutes to.
Okay. I'm towards the end. Okay. Yeah, but I want to connect to something that I think will. Okay. It's even efficient. The amount of computation you have to do is very simple. You have a finite number of statistics essentially to keep adapting. Just add a number every time. That's it. Okay. Very simple. The time it takes, very important, is polynomial in the number of players. Despite the fact that the game itself, the data of the game, is exponential in the number of players, you can reach a correlated equilibrium in time that is polynomial in the number of players. So our requirement before that I said maybe it's too much. Well, it was too much for Nash equilibria, but not too much for correlated equilibria. Correlated equilibria, you can reach them in polynomial time. Okay? The amount of information needed is uncoupled, yes? To compute regrets, I have to know what has happened and what my payoff function is, what I got, what I could have gotten. I don't have to know anything about the payoffs of the others. Okay? So, if instead of Nash you do correlated, you can get all the desiderata. Okay? Now, leading to correlated equilibrium means that the statistics of play looks exactly like correlated equilibrium. Okay? Let's not get into that. Now, here I have some things. Okay? This regret matching, now it's very interesting because we got to regret matching from a purely mathematical, essentially from some theorem, then another theorem, then doing some reduction, then thinking a few years about something that we were sure that something like this must work, and never until we found it. Completely, I mean, it's not, we never went like saying, what do people do? Let me try to model that. No, it came from purely mathematical things. And then we got this regret thing, which suddenly is very much connected to what people actually do. Okay? So here is, I'll give you some you probably know this paper, or some cousins of that. So that anybody knows about this? Or it's okay. So it's a very simple experiment. What they do is the following: you are given 2 roulette wheels, okay, and on the screen, yes, and you are asked, and you see various probabilities and prizes that you can get in some way, and you are asked choose one, okay, and then they spin the roulette and you get what the roulette gave you. Then you say, okay, choose one, we spin it and you get it. Now they run the experiment 2 different ways. One way is you choose the roulette, they spin the roulette, and that's it. The other, you choose the roulette, they spin the roulette and the other one also, and you see what you could have gotten had you chosen the other one. And then you look at the sequence, how they switch between the 2 roulettes. Okay? You know, if you win, maybe you stay, win, stay, lose, shift, or various kinds of strategies. You look at the sequence of decisions. So in one situation, you only see the outcome of the roulette you chose. In the other, you see the outcome of the roulette you chose, and of the one you didn't choose. Okay? First of all, those sequences are very different. Okay? Then they try to see what explains the difference the best. And turns out, not surprisingly, there is a certain form of regret. It's not exactly the regret I talked about, but it's very similar. Okay? And in fact, then there is a second part, which has to do with the orbitofrontal cortex, which I think they thought that this probably is done, this kind of computations are done in the orbitofrontal cortex, which I guess is someplace here. So they looked at people that have a cut here, okay, and they did the same experiment with them. What happened is whether they saw the roulette they chose or both made no difference. The same sequence of decisions. So result, the regret is used and it's computed here. Okay. Then again, this is the beginning, and there are many more experiments like this. In fact, yes, this is a much trend in cognitive sciences. That's when was it? It's much more recent. So this is a certain survey where they talk about regret and so on. By the way, another place that probably don't care unless you need to make a phone call. So there is something called cognitive radio. Anybody heard about that? Yes. So cognitive radios are when you have not this. I mean, my cell phone, or all these beepers and so on. I mean, there is a bounded bandwidth, and if everybody wants to talk at the same time, I mean, there's going to be a problem. Okay? So how do we solve it? Well, every phone and so on, calls the central bureau, the central director, says, I want to make the phone call, so give me a line, or give me something, you know, and of course that can't work with the quantities that we have. It's not going to be efficient. So the other thing is you're trying to do it using some local information. Okay? And cognitive radio is exactly taking a phone and putting some chip inside that essentially does some simple computation based on information of what happens around in a small neighborhood. Okay? And again, it's a whole area, turns out, and I don't understand what they are doing, but look at this. This is beautiful. You see, the exact tracking, which is exactly the exact matching, gives you 80% efficiency. I have no idea what they are doing. I read it 3 times. I get some feel to it. I still don't understand what they are computing there, but it looks nice. So I don't know. Maybe somebody else can help me. But okay, so it's using exactly the algorithm of the dynamic of regret matching. That again, so it comes from completely theoretical considerations, and apparently using something like this is very good. I don't know. Okay, other things like this. Yes, that's something with statistics. I won't talk about that. Okay, so now it's good time to okay, this is mine. I won't talk about that. But okay, here is. I won't talk about that either. I think that's okay. So now let me just tell you something where I come from or where this belongs. This is the last slide. So essentially, the kind of program to which the research I talked to you about belongs is there are lots of dynamics out there. And everybody can come with his own idea of look at a nice dynamic and this is going to give us optimization, Nash equilibrium, whatever, and so on. Well, maybe, okay? So what we want is to know what kind of dynamics work and what kind of dynamics don't. Can we somehow take this huge class of dynamics and start drawing borders and saying, look, here are dynamics that no matter how smart you are, in this class of dynamics, you are never going to get what you want. Now you'll be surprised how many PhD theses in retrospect, and how many even papers in leading journals have been published of the sort, look at this nice dynamic that I found. It works beautifully for 2-person zero-sum games, for 2-person this. It even works beautifully for the Shapley example, which is a special kind of game. It's quite a simple game, but it's a stumbling block for many dynamics. Conjecture, by the way, I can't prove it for Shapley example, but here is a nice Excel simulation. You see how it works, okay? And conjecture it works for every game, I just can't prove it. Now we know. No, you can't prove it. It's wrong. You are in the wrong class. This can never, such a dynamic can never do what you play. Okay? So we're surprised retrospect how much work of this could have been saved had we known this before. So anyway, knowing that we have this huge class of dynamics and we can say, look, if the dynamics satisfies this and this and that, no way, you can't get to equilibrium here. Don't prove. Here, maybe. So here you can't, here you can. Now, here you can. That's the right class to look for natural and nice dynamics that tell us something. Yeah, that have some insight, that tell us something. Okay, so that's the kind of research where this belongs, and I think we get some misunderstanding of some of these borders. Okay, and I think that's about yes. I wanted here to have a basketball rotating, but it's too much for me. So that's the best I can do.
Can you tell us about NBA?
About?
The relation to NBA?
Yeah, sure, okay. I hope this comes to that. Yes. So, well, I was in Boston. There was Boston, Nyberg, Parrish, McHale, Dennis Johnson, Danny Ainge. I mean, this was, almost the best team. It's not the best NBA basketball. Yes, I'm talking about basketball, Boston Celtics. Now, going to see the game in the Boston Garden, the old Boston Garden. I saw it there, where, you know, the story was that the floor there is not straight, and only the Celtics know exactly the different slopes, and they know where from here if you shoot, you do this. Okay, story. Okay, nice one. Anyway, but seeing the game there, suddenly usually, so Larry Bird gets the ball, okay, and the Celtics attack. Let's make it very simplistic. They could go attack on the left or on the right. Okay, now I'm pretty sure, I didn't do the statistics, but, you know, I mean, in American sports, they do more statistics than play. So there are statistics, I'm pretty sure that the Celtics half the time attack on the left and half on the right. Because were they to attack more on the left than on the right, then of course the defense would be more on the left than on the right. Okay? So it's half-half. But somehow, they always knew where they are. Larry Bird didn't have to, where is McKay? Oh, there's McKay. No, that's not how it works. Larry Bird will get the ball, will throw it there, McKay will be there, punish and basket. Well, not always, yes, it's not 100%. But somehow, there was a beautiful coordination between the players. They knew where everybody is going to be and what they are going to do. From the point of view of the opponents, it was half-half, whether it's left or right. They knew whether they are going left or right. How do they know? The first step of McHale, or the finger of Larry Bird, I don't know. You ask them, I'm sure they won't be able to tell you. But they play so much together that they developed some kind of common signals and coordination that they knew with, again, probability which is much higher than a half, where they are going to find one another. Okay, that's what good teams, what they call a team, yes, not individual players, and it's exactly this coordination that from the point of view of the opponents, it's half-half. The opponents have no clue whether it's left or right. They knew much more than half-half. That's again a nice correlated equilibrium. Yes? And in fact, it's funny because when I told Aumann about this, and he said, you know what? That's exactly how I started thinking about correlated equilibrium. One team against another, each one correlating among themselves. But then I realized, Aumann said, that you don't have to talk about teams, and you could just get any signals you want, and anybody getting his own signal and do something much more general. But that's really so, things are coming back. Okay.
Are there any other dynamics that lead not to equilibrium but to cycles or to?
Look, there are. Okay. Now, one can talk about generalizations of Nash equilibria. There's some Nash cycles or something which is not clear exactly what there are. There are some things like this which are not. But that means most of the time you're not going to be in equilibrium. Okay? Any kind of cycle you do, no. I mean, Nash equilibrium usually separate generically. There are a finite number of generic and odd number. It's quite odd, but it's still odd. 36 points, yes? So it's an odd number of discrete points, okay? They are not connected. So if you have something that goes through them, I mean, most of the time you're not going to be at Nash equilibrium. You're going to be on the way. That's not converging to Nash equilibrium. Nash equilibrium means you get to one of them and stay there or close to it forever.
Why are we sure games should converge?
No, I'm not. No. I'm saying if you want that, you can't get it. So now maybe the conclusion is you don't want that. That's okay. But at least now you know why you don't want it.
No, but that's the question. Why focus on convergence to Nash?
Look, Nash equilibrium is the central concept in game theory. Okay? It's a static concept. It's very natural. If the dynamic was ever stopped, it must stop at the Nash equilibrium. So the rest point of the dynamic is the Nash equilibrium. If you look at any dynamic where you are better replying or best replying or improving your payoff, the rest points, natural rest points where nobody wants to move, is where everybody is optimized, right?
That's a theorem.
If you define things correctly, it's a theorem. Yes, I mean, it's a question of decision. Let's not. No, but I'm saying conceptually,
all the
rest points.
So all the dynamics that you describe, if they go to a fixed point, it must be Nash equilibrium.
I didn't require that. That was not part of my requirement. But if you want, you can add this requirement. Okay, that won't help you because I showed you that you can't do it even without a requirement. So adding more requirements can't help you. It will only be once. But I'm saying natural dynamics. I mean, if you think about you have a static concept, okay, which is a very good static concept. I mean, good for applications, theoretically application, whatever you want. The concept of Nash equilibrium is a very strong concept. Okay, it's a static concept. It tells you if you are there, nobody moves. Nobody has any incentive to move. Okay, question, can you get there? Sure, let people optimize and you get there. Answer, no, you can't. It doesn't work this way. It's a fixed point. It's a very difficult, what we learn from this is that this concept, which statically, it's a very, very simple and appealing concept. Dynamically, it's a very, very difficult concept.
So the question is, what is the step? The question is, so let's go beyond. So this is a bad concept. So what is the concept that replaces it?
Correlated. Okay? If you want, that's one suggestion. Yes, that's one suggestion. Correlated equilibrium is a concept that has very strong foundations. It's a static concept. In terms of incentive, in terms of everything. In terms, as I said, think about the world around you. You have all the signals around you, so they'll find their way in equilibrium. Okay? So this is a much more natural concept. Also, it's a dynamically simple concept to reach. Okay? It's easy to get them. Okay? So yes, the answer is correct. In fact, some game theorists, I mean, I know at least one game theorist that is willing to bet on the following, that among all the universes where game theory was developed, you know, Alien universe and so on, more universes started with correlated equilibrium before Nash equilibrium. So we are the outliers. Now we have, I don't know how to check the fact yet.
The universes are correlated?
I don't know, yes, but so, you know, it's, yes, correlated, yes. So if you want, it's, I'm pushing for correlated equilibrium rather than Nash, because dynamically Nash is extremely, it's appealing, but it's very hard to get there. Correlated, it's no less appealing, and it's very easy to get there.
Last question.
Sorry, if the players were in the same? What do you mean, were in the same? In terms of how they play, if they're optimal or not, their memory or not. Look, the impossibility is, even if, no, so in fact, that was a slide that I skipped, which goes the following. To get to Nash equilibrium, you need some coordination between the players in the dynamic. It's like we talked about the dynamic that works, everybody has memory too. Okay, it works if everybody has memory too and everybody does what I tell them to do, what they describe to you. Okay? If one of them doesn't do it, he does something else, it's not going to work. So you need a lot of correlation, a lot of coordination, let's say, in the dynamic itself, in the way they are playing. So to reach Nash equilibrium is not just difficult per se, it also requires the players lots of coordination. For correlated equilibrium, no coordination is needed. Everybody can sit at home, do his own, and the whole thing miraculously goes to correlated equilibrium. Okay? I don't know if this answers the question, but at least it was a good point, a good place for me to plug in something else. So, so if it doesn't, I mean, I'll try again. Again, it's to get to correlated equilibrium, there are lots of dynamics that work. Each player could play a different dynamic, they play a different regret strategy, and there are lots of things like this. Doesn't matter, it's going to work. For Nash, they have to be very coordinated. So there was even the slide that I didn't show, there was something called the law of conservation of coordination that says you either have to have coordination in the solution concept, like correlated equilibrium, or if not, then in the dynamic, like Nash. Just as a physical law.
I think we should end here and thank our speaker.